A free energy developer who lives in South Africa and who prefers to remain anonymous has very kindly shared the details of his compact self-powered generator so that you can build one if you choose to do so. This is the third video in this series, and you'll find the first two videos on this channel. The original design started with 40 watts of excess output power from a self-powered generator. The design was developed on from there to give 60 watts and then 150 watts, and then it was further advanced to have a smaller, simpler, cheaper version which produced at least 150 watts. This version here is a further advance. It's the 150 watt generator, but in solid state. That means that it doesn't any longer have a rotor and movement in the operation. The original designer used an accurately made rotor with 5 magnets spinning inside a ring of 10 coils. This was a very successful design, but his designs are fine for people who've got good constructional skills and access to suitable equipment. However, it's always been desirable to have a motionless, solid-state version which generates excess power without moving parts, or without the constructor needing to have good skills and equipment. The next step, moving to solid state, comes by applying common sense to the earlier designs, which have proved very satisfactory in operation and in output. If the latest rotor version produces 10 pulses per revolution and rotates at, say, 2,500 revolutions per minute, then the circuit generates about 2,000 times 10 divided by 60, which is 417 pulses per second. That's normally written as 417 Hertz or cycles per second, which is a low rate for an electronic circuit, although it's a major rate of mechanical rotation. The circuit generates its excess power by applying these 417 pulses per second of 12 volts to 2 chains of 5 small coils in each chain. The circuit uses 2 separate Hall effect sensors. This is a circuit here, and there are 2 sets of coils wired in groups of 5. There are 2 sensors positioned around the rotor. That works very well indeed, but if we want to reproduce this performance without the rotor and its magnets, then we need to apply 12 volt pulses to those 2 chains of coils 417 times every second. That may sound difficult if you're not familiar with electronics, but in actual fact it's a very simple task, and 417 Hertz is very slow operation for an electronic circuit, as they could easily generate 3 million pulses per second. Because we live in an intense energy field, when each of those 12 volts pulses is cut off, the voltage across the coil chain rises very rapidly to more than 600 volts, and that causes an inflow of energy into the circuit from our local environment. That inflow of energy is much greater than the original 12 volt pulse, and that is what we call free energy. The latest coils used with the rotor system are wound 12 layers deep and 27 millimeters long on galvanized iron 6 millimeter diameter bolts. There's a common conception that iron can't change its direction of magnetism very fast. Personally, I'm not at all sure that that's actually correct, but initially let us presume that we need to keep the pulsing down to, say, 800 pulses per second or less. Of course, if we're winding coils for this solid state project, then we could wind them on a ferrite rod as the core, as that should allow a much higher pulsing rate, and it's reasonable to presume that the greater number of pulses per second, the greater the average excess output will be. Initial tests have been carried out using the existing 10 coils which were used with the rotor circuit. The output proved to be satisfactory and pretty much equivalent to the rotor circuit output if the driving signal in the pulsing was 40% on and 60% off. That is a 40% duty cycle. Just initially we will stay with low frequency due to assumed iron core coil limitations and run the test using a circuit of this type. In this circuit here we have the battery powering the circuit. We have a 555 standard timer. The power supply to it is from a capacitor fed by a diode, and it's a very simple 50% duty cycle circuit with the resistor R and the capacitor C determining how fast it runs. The 10 nanofarad capacitor here connected to pin 5 is just there for the stability of the 555 chip itself. Now the output from the 555 timer is from pin 3, and it feeds to, in this case, just two field effect transistors. They are of type IRF 840, and each of the transistors is driving a row of 5 small coils of the type that were used for the physical rotor design. The output on the drain of the field effect transistor is pulled up very high in voltage when the current is cut off, and that high voltage turns these diodes upside down and they feed current back into the battery, and the battery itself powers a load, which in this instance is the original 150 watt inverter. That gives you mains voltage and mains frequency as an output from your little circuit. The developer has powered both coil chains of his rotor circuit from a single transistor, even though they generate at least 600 volts in feedback pulses. He used just one transistor for his tests. He also likes to use his circuit which swaps over two drive batteries, one battery to provide current to the circuit while the other one is recharging, but that arrangement is just a minor matter. So let's say for argument's sake that the above circuit is running at about 500 cycles per second. For that the capacitor might be 100 nanofarads or 0.1 farads and or 0.1 microfarads, and the resistor R might be 1.5 K. In order to keep the coil frequency down, then there will be some 500 pulses per second returned to the drive battery. But if we were to connect the circuit like this, and to a quick glance it looks pretty much the same, but it isn't, because the second transistor is being fed from the first transistor. That means that the second transistor will not switch on until the first transistor switches off. When the first transistor switches off, the voltage goes high, cutting off the current through these initial chain of 5 coils, and that gives a high voltage fed to the gate of the second field effect transistor. That switches it hard on and applies the full battery voltage through the coils and through the transistor back to the battery. And that means that when transistor 1 is on, transistor 2 is off, and vice versa. When you do that, the circuit returns twice as many pulses per second to the drive battery, but it does it without increasing the rate of pulsing of either of the coil chains. They turn on and off at their original rate, but they just do it alternately. Remember also that the transistors are powerful enough to drive several coil chains simultaneously, and each extra coil can be expected to increase the excess output power available. However, testing shows that the output from the first transistor is not very good for switching the second transistor on and off, so a better result is produced with the addition of a monostable circuit, as a monostable circuit allows you to specify exactly what length of voltage pulse you want for the second transistor. This is the same circuit but with the addition of a monostable 555 timer chip. That gives you a fixed length of output. Now the values here are just suggested and passing. You need to check and test the values that you want in your circuit, which would depend on a number of factors. But the idea of keeping the coils pulse slowly while increasing the rate of pulses passed back to the output can be extended further. It's perfectly possible to cascade 10 or more coil chains during each of the 500 pulses per second. That raises the output pulse rate without raising the coil pulse rate. This can be done by using a divide by 10 chip such as the CD4017B, which can be wired to act as a divide by 9 or a divide by 8 or any of those values down to divide by 2, and that's achieved by connecting the reset pin, which is pin 15, to the next output in the sequence that you're looking for. So if you are doing a divide by 3 arrangement, then the divide by 4 pin, which is output number 4, which is pin 7, is connected across to the reset, and when 4 triggers, it immediately pushes the chip back to output on pin number 1, output number 1, which is physical pin 3. So it's odd the way they have the pins arranged, but I imagine they know exactly what they're doing. When you're doing that, obviously the 555 clock pulse is speeded up by a factor of 3, because it's going to take 3 times as long before the high voltage output of the chip returns to output 1. The chip connections are shown there in this particular diagram, and the arrangement for the circuit just for example, with 3 transistors driving 3 coils. Now the coils are different. They're wound to the size that you find best for giving the sort of output you want, which means they will be bigger coils, and some experimentation is needed to see how big an output you can get from any one coil. But this is the arrangement here. 5-5 timer, as before, is tripping along steadily, even pulse rate, with a resistor and a capacitor which you choose, and that drives the input on pin 14 to this divide by 10 chip here. Pin 15 is the reset pin of the divide by 10 chip, and in this instance pin 7, which is the 4th output, is connected to pin 15. The transistors then fire one after the other because they're each connected to a separate transistor. So this is the way that the thing actually operates. But I suggest that you connect a heatsink to any transistor you decide to use. But please remember, this is a high voltage circuit, and whatever transistor you're using they have a voltage limit on what they can handle. The RF 840 has in theory a 500 volt maximum, but with these fast pulses in this circuit they operate quite happily with a 600 volt pulse. But please remember that if you're going to use something like a TIP 3055, which is 60 volt, or the NE555 or similar timer chip, it can't handle more than 15 volts input. So you want to be careful, because both that and the CD4017B can't handle as much as 24 volts. So please remember that you need to be careful to drop the voltage to any of those devices if you're going to use them. If it happens that the particular construction of the circuit you're doing works better at higher and higher frequency clock pulses, and that results in driving each coil that results in each coil driving transistor needing a longer drive voltage than the length of one divide by n clock period. In other words, these fast pulses here might not be long enough to switch the transistor on satisfactorily. Now you can do that, you can get around that quite readily if you use a monostable on every output line of the divide by 10 chip. Mind you, the divide by 10 chip can be cascaded and you can have as many divide bys as you want. But the way that it operates is the first pulse here triggers output 1 from the divide by 10 chip. But if you trigger a monostable of longer duration, that'll hold the first transistor on for nearly 4 pulses in this example. And when pulse 2 happens, it will hold its output on for about 4 pulses, and so on with each of these, which means that when you get down towards the end of this lot and you've got coil 8 operating, it will overlap the next pulse to coil 1, and you have at that point 2 outputs driving 2 transistors, and when this one number 10 outputs, you have got 4 coils actually powered: coil 1, coil 2, coil 9 and coil 10. So you can, if you want, control the output to your driving transistors in any way you choose to do. You've got complete control over this. But now that we have no need to construct a precision rotor with magnets, the only significant task we have is to wind the coils. These coils generate the excess power. It's perfectly possible to wind perfect coils without any equipment at all. First you need to choose the wire diameter and buy in the wire needed. Wire of 0.71mm diameter is popular. That's standard wire gauge number 22 or American wire gauge number 21. And wire of that size is easy to work with. It doesn't get tangled up and it's quite flexible. Then you need to choose the core material. Iron, definitely not steel because it becomes a permanent magnet, or ferrite can be used as a core to create a spool by attaching stiff flange discs, in this case of about 30mm diameter, at the ends of the core for iron. The coils shown here are wound on 8mm iron bolts with a winding length of 75mm long. 8 layers of wire and 40mm diameter flanges, which could be a lot smaller, make up the setup for this type of coil. 3 of these coils can be wound from a single 500-gram reel of 0.71mm wire, and the iron cores can certainly operate at more than 6,000 cycles a second. Each of these coils has about 315 turns and has a DC resistance of 1.6 ohms. However, ferrite is generally considered to be a better core for high frequency operation, and these can be wound quite easily using the same 7.71mm diameter wire and 140mm long ferrite rod of 10mm diameter can be wound quite easily without any equipment, and 6 coils with 3 layers each can be wound from a single 500-gram reel of wire, and each coil has about 590 turns. The resistance is about 1 ohm when you do that. The basic ferrite rod has a 20mm diameter disc of stiff cardboard glued to each end. This is what it looks like. This particular ferrite rod had got 2 flat surfaces on it, but that doesn't matter at all. What you do is you cut a 40mm long or 40mm wide strip of paper and mark off 32mm along its length and cut it off. This matches the gap between the cardboard flanges. Then you put a strip of sellotape on the paper so that it overlaps by half of its width all along the paper strip, and set it aside until the first layer of wire has been wound. You can hang a full spool of wire on a rod hung from the edge of a table or a desk. Push the first few inches of wire through a hole put through the flange. Do it near the core and start winding by turning the spool in your hand. The winding needs to be done carefully so that the turns lie cleanly side by side with no gaps between them and no turns overlapping any other turn. This is a desk, and duct tape has been used to suspend a dowel rod on which is sitting the reel of wire supplied by the supplier. This is the 140mm wide strip of paper, and this is the sellotape strip along its length, and the start of the winding is shown here, and it gets pushed in tight before you take it further than it is at the moment. This is a very effective way of winding the coil itself. When the far end of the spool is reached with the windings, you then stick the piece of paper to the layer of turns using the sellotape which is already on the paper. Bend the paper around the layer of winds and pull it tight, using other strips of sellotape pulled in this direction across the width of the coil. The paper will not be long enough to go all the way around the coil, the coil winding as it's shown. This is quite intentional, because you don't want more than a single layer of paper, because all that does is make the coil thicker and requires more wire for the same number of turns. You will need the paper layer to allow you to see the next layer of wire clearly as you wind it. If you don't have that paper layer, it's enormously difficult to see the next layer well enough to detect winding errors, as the wire you're winding with is exactly the same color as the first layer, because the first layer is made of it. You now have a perfectly wound first layer. Before starting the second layer, cut the next strip of paper and make it 40mm wide. Stick a strip of sellotape along the length of the paper again, with half of the width of the sellotape overlapping the paper, and set it aside. Wind the next layer in exactly the same way, in the same direction, and finish it by securing the paper round the core and sticking it with bits of sellotape again in this direction around the coil itself. You repeat the process until all the layers that you decide to put in your coil have been wound. As we decided to use 3 layers, we don't need a third piece of paper, The second piece of paper lets us see how we're winding to make sure that we're getting it neat, and the arrangement here gives you then what is a nicely wound 3-layer coil, and at the finishing end, which will be the far end from the start, you punch a hole in the coil, in the spool flange, and pass the wire through it to finish the coil. You then bend the wire in tight against the flange to stop it slipping. It is important to remember to leave enough wire spare so that you can connect the coil at each end. You can't have too much wire sticking out, because you can always cut it off if you need to, and the amount of wire used in that is not important, because you're winding roughly 23 meters of wire in each coil. The generator itself can be built in thousands of variations, the main difference being the coils used, the core material, the core length, the wire diameter, and the number of layers wound. You can, of course, start with just one coil and see how your circuit performs, and later on add one or more coils to boost the performance. The way that coils perform is not at all obvious. It's generally agreed that the larger the number of turns, the greater the voltage produced when the coil is pulsed. But other factors are also important. The impedance of the coil, that is its AC resistance, makes a very big difference when the coil is being pulsed. That is affected by the core material, the wire diameter, the wire material, the number of turns, the quality of the winding, and how spread out the turns are, and the number of layers, and so on. Generally speaking, it's probably best to wind a series of coils and test them to see which works best for you, and then wind the remaining coils to match your best result. If you wish to use two separate drive batteries, one to power the circuit while the other is recharging, then that's perfectly possible. Batteries which are providing power to a load don't charge nearly as well as batteries which are not providing a load. The batteries which are quite separate and disconnected charge much better than ones that are providing a load. The ones providing a load will charge, but not as fast. However, the mechanism which switches between the two sets of batteries needs to have extremely low current draw in order not to waste current. One possibility for that would be to use a latching relay like this one here, which is very small. It's got two coil windings inside it. If you pulse one coil, then the switch is set to one set of contacts. If you pulse the other coil, then it is reset back to its original state. It's the electronic version of a mechanical two-pole switch. While standard 555 integrated circuits can operate with a supply voltage down to 4.5 volts, and in practice most will operate well at much lower supply voltages, there are several much more expensive 555 chips which are designed to work at much lower supply voltages. One of these is the TLC 555, which has a supply voltage range from just 2 volts right up to 15 volts, which is a very impressive range. Another version is the ILC 555N, which has a voltage range of 2 to 18 volts. Combining one of those chips with a latching relay produces a very simple circuit, as the 555 timer is exceptionally simple. The capacitor used to drive the coils in the relay have the advantage that when voltage is applied to them, the capacitor passes the voltage through to the coil, but the capacitor charges up fairly quickly and the power through the coil is then dropped off. That makes the relay switch to the other state, and you can use an inverter here very simply to drive the other coil. But the trouble is the capacitors are charged up, and that's okay if the capacitors shown here in blue are poor quality and their charge bleeds away in a period of 5 minutes. But nowadays even cheap capacitors are often much too good to allow that to happen. So we need to connect a resistor across each of these capacitors to bleed off the charge and get the voltage to drop down off the capacitor. A value of say 18k would be a reasonable choice for resistor. The resistor is always across the battery, but an 18k resistor with 12 volts across it only draws 2/3 of 1 milliamp of current. So if we prefer, we could use that circuit, and if we want high power we could use a couple of TIP 3055 transistors to boost the switching power of the contacts in the relay. So there's a physical layout if you feel that you need one. The TIP 3055 transistors are only there to raise the current carrying capacity of the tiny latching relay. Let's decide to build a very simple version of this circuit, but allowing for later expansion for greater output power. Let's try this circuit arrangement. The two transistors are driven together at the same time, and there's a great range of operating frequency that you can test out by making the resistor of the RC's combination a variable. The resistor could be 47k or 50k. It depends on which supplier is doing the manufacturing of the variable resistor. The 1k resistor is to stop you turning the resistor value of this right down to 0. If you turn the 47k down so that there's no resistance in it, there's still a 1k resistor feeding the capacitor and keeping the circuit running steadily. You might, if you're an experienced constructor, have your own preferred method of construction, but here we might choose to use a simple layout on an open board in order to make it easy to see what's happening and to give good cooling during the development stage. Perhaps something like this. This is the board, and on the board you have mounted a 12 volt 12 amp hour battery and an inverter to give the output. Your timer circuit there, which is the circuit above, is attached to the board, and the field effect transistors are there, and the coils are all connected to a common point here. This keeps the soldering to a minimum and allows for easy alterations as the circuit is extended for higher output power. The timer board can be swapped out later on if you decide to use a divide by n style of operation. Two types of screw connectors are used. One type has all of the connectors connected together so that many wires can be connected to a single point. The incoming wire goes there, and the fan out to lots of different wires comes through the other connectors. This one has got 16 output connections. There's another one with 8 output connections, but as they're both the same price, you might as well get the 17 hole version, the one with 16 fan out. Unfortunately, these sort of connectors cost about £5 each, which is several times more expensive than the standard connector, which has each connection insulated from all of the other connectors in the block. If cost is a major factor, you can use a standard connector strip and convert it to a single output, multiple output strip by wiring one side of the connections with a thick piece of wire that connects all of these connectors together in one go. That gives you this side to be the equivalent of this arrangement. This one, of course, is preferable in that it's a higher current capacity and so on. Mind you, you don't need much in the way of current capacity here. We have a difficulty in connecting FET or field effect transistors using screw connectors because their pins are so close together that they don't fit conveniently into a screw connector block. We can get around that problem by cutting one connector off the block, bending a central pin of the FET upwards into a vertical position, and using the single cut out section of the connector to make the connection to the central pin of the FET. The layout of the timer is not at all critical, and a layout like this might be used. That's the circuit, and this is a suggested layout. Is the positive line coming in through a diode to a capacitor, which is in this case suggested as 1000 microfarad 25 volt, and that then feeds the power to the 555 chip using connections from pins 8 and pins 4. 8 and 4 go to the positive side. You have also then got pin 1 connected to the negative line, and pin 5 is connected through a 10 nanofarad capacitor down to the negative line to give the 555 chip stability. Pin 3 is the output, so pin 3 gets a jumper, wire jumper, to the output line, and the 50k or 47k, whichever, variable resistor is connected through the 1k resistor to the combined connection to pin 6 and 2 of the 555 chip. And finally you have capacitor C, which you may choose to alter as your testing goes further. For that reason, this capacitor, which is probably the same as this one initially, is positioned where there's plenty of spare room. There are 6 separate connections there that could be made. So even if you were terrible at soldering and couldn't unsolder something, you just cut the wire top and bottom and use one of the connecting points beside it to put in a different capacitor. The capacitor mark C will be about 10 nanofarad, and the variable resistor will be around 50k. It's a linear variable resistor. A higher value could be used if you are looking for a faster rate of speed adjustment. So if you were going to build this generator, how might you go about it? Well, you might start by building the timer board shown here, either as shown or with your own layout. I strongly recommend using a socket for the 555 timer chip, as transistors, integrated circuits and diodes can easily be damaged by heat if they're not soldered quickly. As the generator is for your own use, you can avoid the horrible lead-free solder which is so difficult to work with, and I suggest that 0.8mm diameter multi-core solder is the right size for this work. So to construct the timer board, you're going to need a soldering iron of about 40 watts, a 0.8mm cord solder, lead type, strip board, often known as Vero board, with 14 strips, each with 23 holes. You'll need a drill bit or a knife to break the copper strips which run between the pins of the 555 chip. If you don't do that, these pins all get short-circuited together. You need one 8-pin dual in-line socket for the 555 chip. You'll need some solid core plastic covered wire to form the jumpers on the board. That's the connecting wires on the board. The components you'll need one 555 chip, one 8-pin socket, 1000 microfarad 25 volt capacitor, two 10 nanofarad ceramic capacitors, one 1K resistor, one 50K or 47K or higher linear variable resistor, one diode which can be a 1N4007 or 400 anything really, or a 1N4148 or almost any other diode that you like. Don't get a powerful one like 1N5408 because it's a 3 amp diode and the wire is just too thick to go through the holes on your Vero board. Then you could usefully use a magnifying glass of some type. Cheap plastic one's quite good enough. This helps greatly when you're looking at the underside of the board to make sure that solder joints are well made and that there is no solder bridging between adjacent copper strips, which is enormously easy to do because the spacing is very small. You also need a cheap digital multimeter for measuring voltages and resistance. Not essential, but very, very convenient, is one of these angled arm devices, clamping devices, which are usually supplied with a magnifying glass. If you remove the magnifying glass, the angled arms can hold the board and component in place, leaving both hands free to do the soldering. A cloth wet with cold water is very good for cooling down soldered joints rapidly to prevent heat damage, if, like me, you're not that great at soldering. This is a typical multimeter. It's actually the type that I prefer using. This is an 8-pin dual in-line socket for the 555 timer chip. This is a linear 50K variable resistor. This is the clamping device. This is a 40-watt soldering iron. This is in theory some solder, but it probably isn't much use. And this is the stand to hold the soldering iron. When the soldering iron is in the stand, you can leave the soldering on all the time and it won't do any harm. You need some copper strip board with the strips running along. You cut a piece of this out the size you want before you actually start wiring the circuit. This is a reel of solder of the type and size you want. This is the sort of connecting wire that you want. You want some stranded, that is with strands in it, and you want some solid core. And this is a handheld drill bit arrangement for breaking the copper strips where you need to break them. Very few copper strips need to be broken in this circuit. You start by breaking the copper strips, which are shown by the red dots here. They're on column 10 and column 11 of the board, and they start at row 6, and rows 6, 7, 8 and 9 in columns 10 and 11 need to get broken so that there's no connection between pins 1 and pin 8, and so on down the actual chip itself. So this is the arrangement and layout. You start by putting in the wire jumpers. They're not heat sensitive and they're easy to do, and it's routine, and it gives you practice in making solder joints on the board. If you drill a hole to mount the board on later, make sure that you don't cut the line that's taking the pin 3 output out to the outside world. This position shown here is quite okay, or it could be one lower down. you don't want to cut any of the strips that are being used in the circuit. When you have the wire jumpers put in, you then mount the components, starting with the DIL socket, which you push through the board, turn it over, bend the pins sideways so that they connect with the strips they're going to be soldered to, and then solder the 8 strips. Now the socket is plastic, so give it a chance and do one connection, let the connection cool, and then do another remote connection, and keep the joints that you're doing spaced out and give the socket a chance to cool down when you're doing it. The arrangement itself then is very straightforward. You just work from one side to the other, putting in the components progressively as you go. You then connect the plus and minus outputs, or connecting wires I should say. Their output from the board, their input to the board electronically, and the output which goes to the fan out connector for the gates of the field effect transistors. Finally, you check that the circuit is being connected correctly and there are no soldering errors on the underside of the board. That is much easier to check with a magnifying glass, as the gaps are actually very small. Set the variable resistor shaft to about its mid position, connect the board to a 12-volt source of power, and measure the voltage coming from pin 3 of the 555 chip. In other words, you measure between the negative line and the 555 chip output on pin 3. The voltage there should read on your meter at about half the supply voltage, because it's going up and down very rapidly to plus and minus, and that voltage shouldn't change very much at all when you adjust the variable resistor throughout its entire range. We're now ready to start assembling the generator, getting a suitable board and attaching it to the inverter and the battery. The inverter there has got outputs for USB ports if you want, as well as mains outputs. The battery there is a 12 volt 12 amp hour battery intended for mobility scooters. Those two units can be attached to the baseboard by drilling holes in the baseboard and using string or wire to hold both the battery and the inverter securely in position. And you can screw the little timer board to the baseboard with one screw or bolt, and you stick the variable resistor quite easily to the board itself. That's quite adequate for what you need in this case. You have one of these big connector strips taking the line from the positive of the battery, feeding it onto the inverter, feeding it onto the timer board, and the negative going out to the negative strip, feeding on to the inverter and feeding out to the timer board, and feeding out to the field effect transistors, which both drive current back to the battery through the connector strip and drive the coils to produce the excess output power. The diodes here are 1N5408, which are 3 amp diodes, too big to fit through the holes in a Vero board, but very good very good diodes, and you use 3 of them connected together in parallel to make it easier for the current to flow through them. Now the board is very light and robust, the timer board, so one screw is quite enough to hold it in place. Now some constructors hate the idea, but my preferred method is to use Impact Evo Stick as the glue. It's very effective, and after a day or so it becomes very strong indeed. The separate FETs shown in this circuit with each coil. In other words, one FET is used to drive one coil. It's suggested in this circuit, but as I said before, the South African developer states that he can detect no difference between driving two coils with one FET and driving those same two coils with two separate FETs. Please understand that this presentation is for information purposes only, and it's not an encouragement for you or anyone else to actually build one. Also, no representations are made that this design will produce any particular level of output power. Mind you, you can increase the output power pretty much indefinitely just by connecting more coils and more transistors.